Hello, this is the video that I've prepared to present to the CHM 146 Advanced Chemistry 2 students to introduce you to Chapter 11 material. You should be watching this after taking the first exam of the semester. The video may end up stopping at various points and then being merged so that hopefully it's all one big package for you to watch. But for those of you who were present when we made the lab video, you understand that the camera sometimes stopped recording. So I'm going to try to keep an eye on that and see how far along we get and break up the material into different chunks, and then I'll take care of merging the videos for you prior to posting it. So hopefully what you're about to watch is one nice entire video, but we'll see how it turns out. So Chapter 11 now, we're ready to turn our attention to the other phases of matter. We've already studied gases quite a bit, learned several gas laws that govern the behavior and describe the behavior of gases. In Chapter 11, we are going to look at how the other phases of matter behave to some extent. But before we can do that, we have to answer a very interesting question, which is that now that we know a little bit about temperature and its relationship to energy, I would hope that there's a few questions in the back of your mind, like, well, at a given room temperature, for example, the room that I'm standing in right now, all of the objects have the same temperature. And we did this with heat capacity. We talked about how the table felt different from the leg of the desk that was metal when we grabbed it. But everything was at the same temperature. And temperature is, an approximation of how much energy is present in a system. So, our table has the same amount of energy as the air has in it, as a glass of water has in it. So if everything has the same energy, same amount of motion associated with it approximately, why are we seeing different phases of matter exist at that same temperature? In other words, what is it that allows the oxygen and nitrogen in this room right now to be in the gas phase and acting the way that we know gases do, but yet the majority of water that's in this room would be present as a liquid. Some is vaporized, and we know there's humidity in the air, so there's a little bit of water vapor, but the majority is in the liquid phase. And then yet many other things are present in the solid phase. A piece of copper would be present as a solid, for example. Right? So what's controlling or what's different about those species, those three different substances, a gas like oxygen, a compound like water, and a metal like copper, that's causing the three different phases to exist, even though they're all at the same temperature? And the quick and easy answer to that question is that phase is determined, phase of matter is determined by a number of factors. Okay? Underlying those are the temperature, of course, although we've just talked about how all of the objects in a room like this have the same temperature. Okay? The atmospheric pressure can play a role in this. All right? But the big one, the one that we want to learn about in today's lecture, is the intermolecular force of attraction. I guess you could think of these first two, as temperature and pressure, as things that would be trying to pull a substance apart, or in some sense. They're the energy available, especially from the temperature. This is what's allowing the energy to, quote, pull molecules of a substance apart from one another. Okay? Now, I don't mean to break the molecules. Imagine reaching your hand into a bag of gummy bears, for example, and sometimes the gummy bears are stuck to each other. Your hand is sort of like the temperature. You're pulling gummy bears off of that collection, right? You're not pulling the gummy bear apart and breaking it down into the different sugar components and the color components. You're simply separating one gummy bear from the aggregate group that's present there. Right? That's the different view that we have of our phases of matter. In a solid, our molecules are very tightly packed and they're all in contact with each other. In a liquid, our molecules are still touching one another, but there's a little more space. This is a bit of an exaggeration the way I'm doing it. But they are a little more spread out in most cases. So there's a little bit of more room present in there. And then, of course, in the gas phase, our molecules are completely separated from each other. And temperature is the major player in what moves a substance from this solid to liquid to the gas, or vice versa. But working against the temperature and perhaps the pressure is this new thing that I'm going to introduce today called the intermolecular force of attraction. Right? So when you reach into a bag of gummy bears, they're sticking to each other. But when you reach into a bag of pretzels, the pretzels don't naturally stick to each other. There's no attraction between them that causes them to cluster up in the bag. So there's something different about gummy bears from pretzels. And it might be a little harder for you to pull free one of the gummy bears, whereas the pretzels might just naturally come apart very easily from each other. So that stickiness, that tendency of the foods to want to stick together, would be the sort of the intermolecular force of attraction. So these intermolecular forces of attraction are forces that exist between molecules that hold the molecules to one another. Okay. Again, we want to be very clear. These are not the chemical bonds that we're talking about. All right? I'm not talking about the chemical bonds that are holding carbon atoms to oxygen atoms. I'm talking about what might stick one complete molecule to another complete molecule. Right. Without getting too far ahead of myself, let me draw a water molecule. Okay? So we've got a single water molecule. What would cause this water molecule, by itself, it would be in the gas phase. What would cause it to then stick to another water molecule, in other words? And we'll often represent this attraction between molecules as a dotted or dashed line. So the black, if you could see the difference in colors, the black dotted lines that I've drawn here would be the attractions between two different water molecules. So these are the intermolecular forces of attraction that we're interested in. And there are several different varieties of intermolecular forces, some which are very strong and some which are very weak. The IMFs, intermolecular forces of attraction, just for short, IMF, okay? The strong IMFs tend to, but not always, they tend to lead to solids, okay? Substances that exist in the solid phase, all right? Whereas weak intermolecular forces lead to gases and liquids. Okay? There is not as much attraction between the molecules, therefore it's a little easier at normal conditions that we're used to have those substances pull apart and exist in the liquid and the gas phase. All right? So that's just a real first level approximation right there. Stronger intermolecular forces lead to solids usually. Weak intermolecular forces lead to gases and liquids. There are other variables that play a role in this, of course, and I'll mention those as we come across them. So let's figure out and let's learn a little bit about what the different intermolecular forces of attraction are. The names that we have for the different intermolecular forces of attraction come from terms that we've already used in chemistry, particularly when it comes to the types of bonds that might be present, okay, and what's going on with polarity and non-polarity in molecules. Some topics that we cover in Chapter 9 in our textbook that we're using in Chemistry 1. So if you want some refresher on some of these topics like Vesper and on bond polarity, I would direct you to flip through Chapter 9 and look back into your Chem 1 notes on those topics. Okay? I'm going to do a quick refresher though. So remember that